Recently we were considering the Riemann sums and ways to find the area underneath a curve, and we're going to continue to talk about the area under a curve, but we're going to transition into connecting area and the idea of an integral. So imagine we broke this particular curve, it really doesn't matter what it is, into a few rectangles. And so it might begin to look something like this. And let's say that we wanted to talk about just one rectangle in particular. So let's say that this is some x value. The x value is a. And this is another x value b. So we're going to consider the rectangle between a and b. And we can see that here's the rest of the rectangle up here. Now, notice that a and b are x values, and so if we were going from a to b, then one of the things that we're talking about there, this is the width of our rectangle, going from a to b. And if we were to consider, say, the height of our rectangle at a, right, this is the height of our rectangle. And so we know that the area of our rectangle is, we'll say it's height times width, or length times width. Now, let's translate this a little bit. Notice that the distance from a to b is a change in x values, right? So the width, another way to think about it, is just the change that x is making, in this case from a to b. And our height at this particular, for this particular rectangle, how we're considering it, is f of a. Right, so f of a times delta x is just another way to think about what our area is. Now, we could slice this particular rectangle up into pieces that have smaller and smaller widths, right? So we could bring b closer and closer and closer to a. So what's happening is that our width, the change in x, is getting smaller, or we could say that the change in x is getting closer to 0. Right? And as the change in x gets closer to 0, a way to think about it is it's getting very small, infinitesimally small. And so this idea of dx is related in some sense to the change in x, but it's a very small change in x, and by very small I mean infinitely small. There should probably be an E in here. Infinitely small. So our area under the curve is somehow related to our change in x being very small. And if you think for a moment, this is a limiting thing, because this one rectangle that we've been looking up is really made up of lots of rectangles, in a sense infinitely many rectangles that have a very, very small width and heights at different places. And the idea is that as our width gets small, our height is getting more and more accurate. We're getting it all the way along the curve. And so we're adding up a bunch of rectangles. In fact, it's a summation problem of a bunch of heights times really small widths. And in one sense, you can think about this symbol, the summation, is getting changed into an integral symbol to kind of represent that summation. We'll tie this in a little bit more in a bit, but so our area is related to the integral of our function with respect to x, and we were looking specifically on the interval from a to b. And when we do that, when we do all the infinite number of rectangles that are here, then we'll have an extremely, well, not extremely, the exact value of this area. Now, some things that are important to note is that when assume that a is less than b, so we have to make that statement. If a is less than b, then our width is positive. Dx is positive. And if we're integrating from a to b, then dx will have a positive value. And if we were going in the other order, if we were integrating from b to a, then dx has a negative value. So the order matters, right? So assuming that a comes first in order, or a is less than b, then our dx would be positive in that case, and our dx would be negative if we were going in the other order. The other thing that would happen is if, how do I say this? If f of x is above the axis, remember f of x is a y value, so this really should make sense, is above the axis, then our integral will be positive. And if f of x is below the axis, then that portion will be negative. Right, so if we want to summarize those ideas a little bit in maybe a table, in general you could have something like this: the integral from a to b, f of x dx, and we're assuming that a is less than b. Our outcome is positive if f of x is above the axis, above the x-axis. And our integral will be negative if f of x is below the axis. And finally, these get switched if you're integrating from b to a. And again, that's, no, what am I saying? These don't get switched. Delete that last comment. That the integral, that's a better way to say it, the integral from a to b of f of x dx is opposite in value of that same integral, but from b to a. So we're just going in the opposite direction as far as finding our x values. A couple other facts, and this will make a lot more sense, I hope, with practice. One, if you're integrating from a to a, so your starting and ending points are the same, then the integral is equal to 0. Right? There's no area because there's no change in width at all, no width at all to the area. If you're integrating, as we've already said, from a to b of f of x, then this is opposite in value of the same integral but from b to a, because the direction is different. And finally, if you integrate from a to b of your function and add that to another function that starts from b and goes to some other point c on the same function, that's no different than integrating from a to c, which means that two parts can make an entire thing, and an entire thing can be broken up into parts, depending on the conditions. So that's some ideas behind what we're doing, and in the part 2 of this we'll look at some examples.